Okay, in this video, I'm going to be doing some multivariable calculus problems. And we're going to be talking about changing the order of integration, why that might be necessary, what that looks like. Okay, so I'm going to just start with an example. Okay, I'm going to start with a double integral. Okay, so we've got here, some kind of double integral. And so this is integrating from y over 2 up to 1/2 with respect to x, and then with respect to y, it's going from 0 to 1. Okay. So we know that the first step is to kind of look at the integrand and see, can I cook up an antiderivative of this thing with respect to x? And, if you remember from AP Calculus, you're like, no, I can't. There is no closed form antiderivative for e to the negative x squared. So what I need to do is I need to kind of investigate this region of integration. Okay, this is x running from y over 2 up to 1/2. So x equals y over 2. All right, well, I'm going to deal with that in a second, but I'll deal with x equals 1/2 right now. Okay, we know what that looks like. That's x equals 1/2. Okay, and then x equals y divided by 2 is y equals 2x. Okay, so I can kind of plot that line. And I can see that this right here is my region of integration. Okay, in general, my best advice to y'all is to sketch the region of integration. That's always a good play. That can help you if you need to reverse the order of integration, which is what I'm going to need to do right now because of e to the negative x squared not having a closed form antiderivative. So what I'm going to do is I'm going to have to start with respect to y. So y is running from, here I'll just kind of try to draw a little representative rectangle, running from y equals 0 up to y equals 2x. Okay. So y goes from 0 to 2x. And then x is going from 0 to 1/2. So that's going to be 0 to 1/2. And I'm still integrating e to the negative x squared, but now dy and then dx. Okay. So I'm going to start off, and I'm going to look at the integral from 0 to 2x of e to the negative x squared with respect to y. All right, well, and this has no y's in it, so the antiderivative with respect to y is just going to be this times y. And then y is going to run from y equals 0 up to y equals 2x. And then we're going to integrate this from 0 to 1/2, and it'll be great. So, at this point, let's put one of these in there. I'm going to plug in top and bottom and subtract, but when y equals 0, the thing's going to just kind of get killed off, so it's going to be 2x e to the negative x squared dx. And this is something that we know how to solve, right? This is u du. So I'm going to go over here, and I'm going to say let u equal negative x squared. Okay. So this becomes, the integral of e to the u times negative du. All right. And so what this is going to be is negative e to the negative x squared. As x runs from 0 to 1/2. And I know I skipped some steps on the substitution or the change of variables there, but it was pretty obvious, and I think at this point y'all know how to do that. Any issues with what I did there? No? All right. Then I will move on, and I will do the, what? It was just u du, yep. But I just did u du on the antiderivative rather than changing the bounds as well. And I'll tell y'all, the more y'all integrate and the less you can just kind of figure out the antiderivative with u du and then just use the original bounds. So this is negative e to the negative 1/2 minus negative e to the 0. Okay, so this is 1 minus 1 over the square root of e. Yeah, definitely. So it would be the fourth root of e then, right? Okay. Yeah, good point there. Yep, did not square that. Okay, so 1 minus 1 over the fourth root of e. Excuse me. All right, the next one I've got is one, it's going to end up playing out very similarly, but you're going to integrate 1 over the log of y, where y runs from e to the x up to 10, and x runs from 0 up to the log of 10. And, okay, so I'm going to start doing the exact same thing. Okay, so it looks like x and y are both positive, so I really only need to look at the first quadrant to kind of pin down my region of integration. Y is running from e to the x up to 10. Okay, that'll be e to the x. This will be 10. Oh, whoops. And then, probably not drawn to scale, but it's okay. Right, and then x is running from 0 to the log of 10, but that's just kind of a consequence because I can see it's the region trapped in here. All right. Now the thing, again, about 1 over the log of y is, I don't know, how am I going to integrate the anti-differentiate this? I don't have an antiderivative for 1 over the log of y. That's just not something we got. Maybe there's one out there, but I sure don't know it. What I'm going to do instead is try reversing the order of integration. Okay. So this is y equals e to the x, and y equals 10. But maybe instead what I should do is, say y equals e to the x. Well, that's like x is equal to the log of y. And y equals 10, we'll hold on to that. But x is running from 0 up to the log of y. Yeah, that's gonna really be it. If we're gonna start with x, okay, we need to think horizontally. And we're going to have x running from 0 up to log of y. Okay, so x equals 0 up to x equals the log of y. Oh, that was not a very good interval. All right, and then in the y direction, what should the lower bound of integration be for y? Should it be 0? Or should it be something else? It should be 1 because that's the intercept of e to the x, or the intercept of log of y. But that's honestly, I mean, y'all are gonna know what to do. That's the type of thing that y'all will trip up on, is that lower bound being a constant, but not the right constant. Okay, so it needs to start at 1 and go up to 10. Okay, and again, maybe I'll let you try to carry out that interior integral. It's going to work out exactly the same, where it's going to require u/du substitution. But I'm going to freeze the screen and let y'all try it on your own, see if you're doing it right. If you're watching at home, you can either follow along with me or just look away from the screen and try this and then check back. All right, so ooh, I might have lied. It's what? Yeah. I think it is. Yeah, I think so. Yeah, no, this one ended up way different than I thought. Well, of course, these are like hand-curated examples. Just only the ones that work out the very best. Yeah, u/du is not going to even be necessary. Yeah, okay, so there you go. Um, I found the results of this one surprising. I thought that somehow it was going to be like, a UDU with x over log x, even though that's backwards, right? It's log x over x that's UDU. So who knows? But this is kind of how it goes when you absolutely have to change the order of integration. There are other situations where you definitely have to change the order of integration, but none are more like right in your face than I don't know an antiderivative for this. Okay, that is really immediately you're thinking, I got to try something else. Okay, there can be issues with the region. If they just say here's region R, integrate over it, you might start with the hypothesis. I'm going to start with Y and then do X and find out that that's not going to work. You can't parameterize it that way or something like that. It's not. I said start with Y, then go to X. So you find your region is not vertically simple or something like that. These are the things that can happen. But this one, when you plugged in x equals log y, you got 1, and then you plugged in 0, and you got 0. And so you're just integrating 1 dy from 1 up to 10, and, well, that's just 9. And that's pretty all right. And I think that that's all I'm going to have for this video. I might come back and record a few more videos as the semester goes on. I don't usually record videos for multivariable calculus, but I thought this was pretty good. And, maybe in the future I have a whole library of multivariable calculus videos.